definition, just so you'll know what's being talked about when these structures and topics come up in the future. Here is the first one. Try to do less time.
100 years ago, scientists believed language depended on two key areas in the left hemisphere. A region behind the ear, identified by a German doctor, Karl Wernicke, seemed to be responsible for overall meaning. It handled word selection and sentence construction. An area further forward, found by a French doctor, Paul Broca, was thought to control the last stage of generating speech sounds. Since then, a far more complex picture has emerged.
Ladies and gentlemen, I'm pleased to participate in this evening's discussion of health consideration in the development of energy sources. These considerations have been with us for some time.
Dr. Wilson Talley, award-winning nuclear physicist, scientific advisor to the American government, will never be able to speak like this again because he suffered a stroke.
Nuclear energy.
Much, very nice. It's March 1998, stroke, March the 6th, sleep. And here about 2 p.m., I got up, the bathroom was here, I went, found this and very strange.
Dr. Talley has a great deal of difficulty understanding anything that is said to him, or even things that he reads. And he also has a great deal of difficulty in producing language. Now, what happens when he tries to talk is that the words come out very fluently, but what he says doesn't have all the content to it. He has difficulty in finding the words that he wants, and he has a great deal of difficulty also in producing sentences that are coherent, that really reflect what it is he wants to say.
A brain scan revealed that a hemorrhage had destroyed large parts of Wilson's left hemisphere, including the whole of Wernicke's area. Nina Dronkers has assembled a unique collection of brain scans of stroke patients with language disorders. It turns out that many have indeed damaged the two classic language areas, but the broader picture reveals a network of many different brain areas which handle specific aspects of language.
We've seen that there are certain patients who have a great deal of trouble really just naming things. We've found patients who have difficulty understanding grammatical rules of language. All of those different kinds of patterns tell us, first of all, that the process of language is incredibly complex, and also that there must be many different brain areas that subserve each and every one of those different functions.
Touch the white circle.
Patients often seem to recover some of the basic aspects of language, like the ability to recognize word sounds, which suggests that these functions don't require their own specialized brain structures.
Touch the green square.
Unfortunately, we rarely see complete total recovery in our basic patients.
Thank you.
And the fact is that in most of them, a fairly significant amount of brain has been affected by their injuries. And that it is difficult for other brain areas that have, for such a long period of time, been doing something else, to suddenly take on this new function. And what we think happens is that the remaining brain areas try to take on this task of language, but they do it in their own way. And unfortunately, they're not as good at it as those left hemisphere language mechanisms, because they haven't been doing that all of those years.
This is very short, but there are a couple of important things to get about this. One, I told you about, I think anyway, that people kind of overdo what they expect we can get from studying neurophysiology. But this is one of the things we can get from it. This is an important finding, because what is happening, if you notice, guy's personality seems fine. He seems like a perfectly ordinary, likable guy. he seems to have some concept of what he wants to say. So the processes that come up with the ideas seem okay. And he can say words. He can access his vocabulary and produce the words for simple ideas. But what he can't do is access the rules for putting sentences together. He can't find the grammatical rules anymore, and so he just says isolated words. What that tells us is there's one part that determines the personality, that handles personality type stuff and friendly type stuff, which was unaffected. There's another part that handles vocabulary, another process, another part of the brain that handles vocabulary, and kind of had some effect there, but not much. And then there's another part that handles the structure of sentences. We have no clue how complicated sentence structure is because we do it all the time and we're so good at it. Until we lose the ability to do it, and then all of a sudden you see what's missing almost completely prevents speech. So this one thing this tells us is that these different cognitive processes that we're talking about aren't in the same place. They're in different parts of the brain, and therefore they must be different processes. That's an important finding. Doesn't tell us much about grammar, doesn't tell us much about clauses or phrases and that kind of stuff, but it does tell us that it's something different than things that happen in other parts of the brain. I had this happen to me once, just temporarily, I hope. But I got bitten by an infected mosquito in Mississippi, and this just happened 2-3 years ago, and I got encephalitis, which is an infection of the brain, which can be very serious or temporary depending on what part gets hit by it. But I woke up, came into the dining room, my wife was already sitting there, feeling really strange. And when I started talking, it was like this guy. Talk. Words. Can't. Talk. Can't. She said, I think it's time for a trip to the hospital. And I said, but here's what it felt like. I could get sentence-size ideas of the idea I wanted to express, and I could even break them down into subjects and predicates and something close to phrases. But there was just no communication of that idea with my vocabulary. None. That's one of the most frustrating things I've ever felt, but it just tells you two things. One, how complicated processes are that we take totally for granted, and two, that they take places in different parts of the brain, so they must be different processes.
I had encephalitis when I was 8 months old, but what happened to me was my muscles. It affected my muscles, like I don't have muscles in my thumb, and that's how it affected me.
It's just whatever part of the brain it hits. Mine went to the back, fortunately, so I will never, ever be able to take another field sobriety test. If you get an email from me saying I'm in prison, it's because the state trooper thought I was so drunk I couldn't walk. This is where you walk the straight line.
Yeah.
I can kind of do it now. That's controlled by a structure right at the back of the brain. And I practiced and practiced and practiced and practiced and practiced. I went in and told the doctor, look at this. He said, that's very good. Now do it backwards. That seems to be permanent. I just can't quite get that specific kind of balance again. That's okay. That's cheap. I'll settle for that very well compared to the other things that could have happened. But anyway, that kind of thing at that level does tell us a lot about cognition. Now the other one I kind of told you about before we started it. Keep in mind that this woman is awake. She's having brain surgery while she's awake, so she can help, so she can talk about it. And she can do that because the brain doesn't have any pain sensors. The brain cannot feel, its own pain. It feels pain for every place else in the body, but not for itself. When you have a headache, that's supporting structures. It's not the brain itself. So what they're trying to do is make sure they're getting the right place. She's got a brain tumor, and they want to make sure they cut out the part they intend to cut out. So they ask her to do things like count, and then they jam that center with a weak electric current, which she can't even feel. But it's like her mouth is paralyzed, but that's not what's happening. Her mouth, she can speak just fine, and I don't want to give too much of it away, but it's like she goes 1, 2, 3, 4, and he touches the center in her brain with the electrode, and she goes and he pulls it away 5, 6, 7, 8, 9, 10. Now that's not, the reason I'm telling you this in advance is I want you to keep in mind that's not jamming her tongue or her lips or her jaws or any of the speech apparatus. She has the concept of fiveness, but she can't translate it into a word. It's translating the idea into the speech sounds that express the idea that he's jamming when he touches her brain with that electrode.
Today, Henry is going to remove a tumour from Sarah Kitchen's brain. It's a delicate operation because the tumour is near a region of the brain that is involved in language. Damage a vital area, and Sarah might never speak again. To avoid this happening, Henry has to do something extraordinary.
We've been going now for about an hour, and the critical phase is coming where they're going to have to remove the tumour. In order to do that, Sarah has to be awake.
If you have a general anaesthetist and go into an operating theatre and have somebody operating on your brain, it's jumping into the deep end with a blindfold on, and you hope you're going to come out the other end in one piece. But if you're actually awake while it's going on, there's a much greater sense of control, and in a way you're part of the team.
What we're going to do now is we're going to get you counting and talking when I touch your brain with an electrode, so we can just work out where the speech area is. Okay?
Sarah, can you squeeze my hand?
Once Sarah's awake, Henry begins to pinpoint the crucial speech areas.
What's your name?
By using tiny pulses of electric current, he can jam temporarily the mental activity going on at a particular site in her brain.
Do some counting for me. I want you to count up to 10 and then back down again. 1, 2, 3, 4, 5.
That's great. It wasn't that she knew the number 5, but couldn't actually say it. She could think the number 5, but couldn't think of it as a number, so to speak. I mean, it's different. It's not paralysing the vocal cords. It's actually paralysing the mental processes that turn a concept, a thought, whatever you want to call it, into a word. Carry on.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Go on counting.
15.
Okay. What's this?
Well done.
Sarah, thank you very much.
Okay, that's that. Turn on the lights. The other one with the guy with the frontal cortical damage, we saw all but the last few seconds of that. But anyway, what we've done here so far is introduce you to the nature of the brain, that it has all kinds of parts that do special things. It's not one single machine where all our thinking takes place. There are lots of places have assignments. And what we've been looking at so far is just the outside quarter-inch or so, the neocortex, which is the intellectual part, which is of most interest for cognition. and especially the frontal cortex and especially the prefrontal cortex, the front of the front, which is where our human intellectual abilities live. Now, you don't think of philosophy or planning your life or what the relationship should be between nations. It's taking place in a part of your brain and being neurons clicking at each other. But it is. And the way I know it is because if you damage it, you can't do that stuff anymore. So somehow, I can't even begin to guess how that's connected to our philosophical and political and personal future thinking, but it is. And that's called the mind-body problem. How is the mind connected to the body? Nobody to this day has, in my opinion, come up with a very good explanation of how that works. There are two more things I want to do before we get off of this. One is I want to pull off that cortex and see what's underneath, because there are some things underneath that are also important in cognition. The cortex, and especially the prefrontal cortex, you can tell from them you're looking at a human brain. No other brain has this big, huge area in the front, not even gorillas and chimpanzees. But you pull that off, and underneath you find a brain that is indistinguishable from, well, any mammal and some sub-mammalian species. It's been there a long time, and it has some effects on cognition. I want to just mention an important part of that, so you know what's being referred to when it comes up. And the last thing in this section I want to talk about is just tell you what some neuroscience techniques are. So when you open a psychology journal and it said that we did a memory study with a PET scan of this person after an auto accident, I want you to know what that means. I'm not going to go into the technicalities of it in any detail, but I'm going to go through the main ones and just tell you in general how they work. But before we get to that, let's look here. And what is called the hippocampus. This is where it is in the brain, except that picture shows it located up and down and back and front to back. What it doesn't show you is that it's buried deep in the center of the brain. And some of it, just so you know, some of the other structures that are associated with it, the hypothalamus, which controls almost any kind of regulation, blood pressure, body temperature, feelings of hunger, all kinds of things like that. The pituitary gland is kind of a master gland for the whole body. It sends out hormones to other glands like the pancreas or the kidneys or whatever to tell them what to do. The amygdala is kind of an emotional gatekeeper. If there's damage to the amygdala, even the slightest surprise will send a person or animal into orbit because they react to it so strongly. But I'm telling you what those are just so you understand that this is a pretty primitive region that we're dealing with. The hippocampus has big effects on intellectual processes somehow, even though it's this ancient structure that's down there in the core with all of these other primitive things. So we need to take a little quick look at that in more detail. I told you the neocortex is a new structure. The cortex in general, especially the prefrontal cortex, is a new structure, meaning only we have it. This is said to be an evolutionarily old structure because virtually all mammals, and even some animals that are not mammals, have something pretty close to it, which is normally taken to indicate that it's been around for a long time. The main thing that damage to the hippocampus, it's not the only thing, the main thing that damage to the hippocampus does is keeps you from learning anything new. It keeps you from forming new memories. That was the basis of the movie 50 First Dates, although they took a lot of liberties with it. She got to remember the whole day. Usually you get about 20 minutes. And it happens because you get whacked on the side of the head somehow, a car wreck, an assault, and the hippocampus is damaged. Our memories aren't in the hippocampus, but our hippocampus does something with new experiences that turns them into memories. If somebody has severe enough damage to the hippocampus, for the rest of their lives, it's the day of the accident. That is, you can introduce them to the same person, say you, 10,000 times, and every time that happens, hi, pleased to meet you. No clue. Some people have partial anterograde amnesia, as that's called. Some people have it complete, but it's really, really, really striking. I've known 2 or 3 people who've had it, and they seem ordinary but a little strange. And then you find out what's so strange is that as far as they're concerned, it's October 15th, 1974, which is when they had the motorcycle wreck. And nothing that's happened since then gets in. So there's something really important to intellectual processes, especially memory, that the hippocampus does. It's not really understood what it is, but it does something. It does something crucial in turning experiences into new memories. Because when it's damaged, we just can't do that.
Yeah, well, what about the amnesia that people get temporarily before the memory totally comes back? What part of the brain?
That's not really understood very well. What you're talking about there is retrograde amnesia, where you've forgotten your past.
Oh, okay.
This is anterograde amnesia, where you can't store any future.
After?
But to answer your question, when people have retrograde amnesia, they may have totally forgotten their past, forgot everything about it, forgotten their name, forgotten who they are. Oftentimes, for reasons that nobody understands, it will come back. But when it comes back, it just happens at random. All of a sudden you remember your 8th birthday, and then later on you remember your high school graduation. It's like these little islands come back. There's no predicting what's going to come back, although there is some bias toward older memories. You don't know how much of it's going to come back. That process is not, even ordinary remembering is not at all well understood, much less the pathologies of it, like amnesia. But anyway, getting it in, the hippocampus is some kind of key, something that's just crucial to that process. It's also the case that if you have a memory, if you experience something and then get hit by a truck a few minutes later, and say some kind of accident that just rattles your head, that will probably obliterate that memory, even though the trauma came after the memory was already in there. If it was a couple of hours later, it'll probably just erase it. If it's a couple of days later, you may remember something happened but can't remember what it was. If it's a week later, you can remember more details, and if it's 3 months, if the trauma is 3 months after the event, it doesn't have any effect on the memory. Something happens to memory after we have an experience, and the hippocampus is working on that experience, turning it into a memory. Something is happening during that period that's like concrete getting hard. There is a period after an experience where the closer the trauma is to the experience, the more disruptive it is of the memory. But if it's a long time after the experience, this exact same trauma won't have any effect on the memory. Somehow memories get more and more and more solid after the experience and much more resistant to disruption by head trauma. Nobody really knows what that is either, but the hippocampus does it, or at least the hippocampus plays some critical role in it, because damage to the hippocampus also prevents consolidation. It doesn't just keep the information from getting in, or even from being registered in the sense that you understand it. But this process of consolidation, where the memories become more and more, solid, if you want to call it that. That does not happen if the hippocampus is injured. Something about the hippocampus is necessary to that process of consolidation. A couple more things about it, just to give you a little clue as to how important this thing is. Even though it's not understood, some things are understood about it. One, I've already said, damage prevents most kinds of new learnings. It especially is disruptive to remembering locations. There is something that the hippocampus does that keeps reminding you where you are. And it's like there is a little map in it, because rats have a hippocampus just like ours. And if you can put an individual electrode in a rat's brain and tell what individual nerve cells are doing, and when if you put the rat in a maze, when the rat is in one part of the maze, one particular cell is going off. Okay, we're here now. The rat walks to another part of the maze, and a different cell starts going off. Okay, we moved over here now. Rat walks to yet another part of the maze, yet another cell starts going off. There's something about the hippocampus that keeps track of location, almost like it's a little map that lights up, reminding you where you are. And that also suffers. Remembering where you are, specifically remembering your location, suffers badly when the hippocampus is damaged. So, another thing, in some unknown way, it performs a really important cognitive function. What I just was now talking about was place cells that only fire when an animal is in a particular location. With different cells reporting or reflecting different places. And then one last thing. Okay, a lot more to the hippocampus than this, but just to give you the examples I'm giving you. One last thing to look at is what the hippocampus has nothing to do with, and that is learning skills. If your hippocampus is damaged, that apparently has nothing at all to learning new skills. You learn new skills just as well as you ever did. You may not learn what they're for, you may not learn when you do them, but when somebody says, okay, just take this and see if you can do it, you learn that skill very well, even without any intellectual knowledge of it. You've probably heard that nobody ever forgets how to ride a bike. That's true. That's really true. Nobody ever forgets skills like that. You may suffer severe retrograde amnesia and forget what a bicycle is. I've seen some tapes of people being tested for this. They'll be shown a bicycle and say, what do you suppose this is? What would you use it for? And they'll say things like, well, let's see, there's a big round thing with the thing. Say, is that some kind of clock? And mean it, not joking. You know, they don't know what a bicycle is. He says, I'm going to give you a hint. This part you sit on, I want you to just sit on this part, the seat. It's called the seat. I want you to sit on this part and just do whatever seems right. Just, use the force. And they do. They ride off on the bicycle like they have never forgotten a thing about it, even though they can't intellectually tell you what it is or what it's for. Those two kinds of memories, where you can declare the information you know, is called declarative memory, and memory for skills is called procedural memory, which is memory for how to do things. They function totally differently. Procedural memory is generally not subject to forgetting. That's why you never forget how to ride a bike. And the hippocampus, while it has to do with learning any kinds of facts or what we would call knowledge, can be absolutely, well, maybe not obliterated, but suffer serious damage, and it's still just as easy for you to learn skills as it ever was. So learning knowledge, facts, events, and that kind of stuff appears to be a totally independent brain system from learning and retaining skills. They just don't use the same hardware. Doesn't disrupt learning new skills. And the terminology I used was declarative memory for facts and events isn't affected by damage to the hippocampus. Affected by damage to many other things, but not the hippocampus. But it does not affect procedural memory for how to do things. We get into this a lot in the memory course because this has a lot to do with amnesia. But for this course, what I'm trying to do is just give you a general feel for how the brain works, for the kinds of things it does, where the sophisticated stuff is, where the primitive stuff is, what the sophisticated things do, what the primitive things do. Just so we can get on with talking about cognition. In that regard, last thing I need to tell you about is technology for studying the brain. Like I just said, you'll hear this stuff referenced all the time when you're reading about any kind of cognitive-related experiment that has anything to do with the brain at all, in which the brain is studied at all. First one is the oldest one. well, not really, the oldest one was see what happened when somebody got shot in the head. But, the oldest one that you really call technology is what's called a CAT scan. Stands for Computer Assisted Tomography. Tomography just means, well, basically taking a picture and taking a picture of the structure. And really, all it is ordinary X-rays that are fed into a computer. Like I had a heart exam last week where they did this kind of thing. His camera just goes, and you lay there for 20 minutes or a half hour while it's taking these pictures from different angles, and then a computer puts them together into a model, which is what the heart would look like if you had it sitting there in front of you. It's often done, depending on what the exam is for, it's done with the brain, and it's done sometimes trying to find out why somebody has a cognitive deficit, or testing some kind of theory about some brain structure. It's really not much advanced beyond X-rays. It's just the computer putting the X-rays from different angles together into a model. And so, all these processes are going to have advantages and disadvantages. This does a very good job of showing the person's brain anatomy, how it's structured, but not ongoing physiological processes. Anatomy means structure. Physiology means processes. CAT scans do a great job with structure. They don't do anything at all with physiology. Sometimes they're still used, not as much as they used to be. Another one, I know I mentioned this basic idea earlier in the course, but you can tell which nerve cells are most active by which ones are drawing the most blood, which ones need the most blood. An active nerve cell needs oxygen and it needs nutrients, both of which are carried by the blood. So if you can keep track of where the blood is going in the brain, you can actually tell what part of the brain is active. So if I ask you to start doing division problems, and I see this part of your brain, all of the blood is going there all at once, I know that's the part we're using. That's pretty good. It's pretty if you can get a hold on where the blood is going, it does give you a pretty good idea of what location in the brain is active. The first way of doing this was what's called a PET scan, or positron emission tomography, where what they would do with this would be actually inject as a shot a small amount of radioactive glucose, which is the kind of sugar that we use for energy. And the level of radiation was so low, I mean, it's not going to give you radiation sickness, or you're not even going to be able to tell that it was ever there. But with powerful sensors and amplifiers, you can tell where that radioactive glucose is going. And specifically, if you're studying the brain, you can tell what part of the brain that it's going to. Based on the fact, as I just said, the harder an area works, the more blood it needs. Molecules that are just really have been made just very slightly radioactive are injected into the blood, and you can follow them. I don't know if he's still doing it or not. Anybody know Dr. Faruqi in biology? He studies pathology. He studies poisons, the mechanisms of the way the poisons work, and he needed to find out how things were being metabolized through the liver. So he used PET scans of the liver to find out what parts of the liver were active. It doesn't necessarily have to be the brain, but in any part of the body, when that part of the body is active, it needs blood. And so you keep track of where the blood is going on. It's really surprisingly good technique for figuring out where the process that's dealing with whatever you're doing is taking place. Problem is, it takes a long time. You can tell if somebody is doing some kind of problem or thinking about something consistently over several minutes, this will tell you exactly where it's happening. But unfortunately, the imaging takes a while. So if you're doing events that just last a few seconds, or especially events that just last a few hundredths of a second, this won't work. It's not fast enough. It's very precise, but only for processes that continue long enough to generate the image. Then the thing that really brought about a revolution in the importance of studying the brain to studying cognition was something we've seen in several contexts already. And that's functional magnetic resonance imaging, fMRI. It's the same idea as PET scans, where in PET scans, you're using radioactive glucose to tell where the blood is going. With fMRIs, you don't need to inject anything, and it's much more precise than PET scans. It's amazing. If you've ever seen MRI image of some part of your body, they're incredible. They're like these drawings they used to do in biology books when an artist would sit down and draw every little detail of a cell. What they're based on is a strong magnetic field, and oxygen behaves. Obviously, this is not very technical, but if you're placed in a strong magnetic field, which is where you're rolled into the big cylinder, and then when the magnetism is suddenly released, you can tell where the oxygen is by what it does, and that tells you directly where the oxygen is going. Also, in general, where the blood is flowing, and that is so precise and so easy to use. The machinery is expensive, so you've got to usually have a deal with a hospital or a clinic. But it is just amazingly good at pinpoint locating. That's why when I showed you the 60 Minutes clip, that was about this. That was about fMRIs. And some of the hopes and concerns for where they may go in the future. The drawback to fMRIs is same as with PET scans. They're faster than PET scans, but they're still not very fast. And a lot of our psychological processes take place on a scale of thousandths or hundredths of a second. And these kind of scanning techniques just are helpless with things that are changing that fast. They've got to have some time to form the image. And as I said, the equipment is really expensive. That's coming down. They're becoming a lot more simplified, but it's still a big issue. Something else, but this will be our last one, that really surprised me when I learned about it, is that anytime you have hundreds of thousands of nerve cells doing the same thing at the same time, they generate enough electricity that you can actually detect it outside the skull. There'll be positive surges, negative surges for different kinds of thinking, generating expectations, having the expectations confirmed. You can actually tell what's going on in somebody's head like that by gluing electrodes to their scalp. You don't even have to break the skin. And there are patterns of known voltage swings that are associated with different kinds of mental events. These are called, now they're commonly called event-related potentials. Sometimes in older literature they're called evoked potentials. And basically what happens is you cause an event to occur, and you track it over the course of the next couple days. You track the voltage changes on the skull over the course of the next couple of seconds. And you're not going to pick up any one nerve cell, but when you got millions of them doing the same thing, and you got a computer that can average that out over several events, you get a smooth waveform, and you can tell from that wave what happened, what just happened. Based on the fact that anytime you have millions of nerve cells acting together, nerve cells always generate electricity. That's what they do. That's what a nerve impulse is an electrical impulse. But if you've got a couple of million of them generating the same impulses at the same pattern, that's enough electricity that if you have sensitive enough equipment, you can actually detect it on the outside of the skull. Paste an electrode maybe here, another one for ground on either your ear or your jaw, and feed it into these really powerful amplifiers, and you can tell. You can tell some of the things that are going on in there using this technique. I just give you a couple of things just so you know what I'm talking about. Although there are hundreds of signature patterns of electrical changes for different kinds of thinking, for different kinds of mental events. But for example, if something surprises you, and I have you hooked up to my evoked potential machine, I can tell that you're surprised because 300 milliseconds after the event, there'll be this positive surge in the voltage on your skull. That P300, as it's called P for positive and 300 for the number of milliseconds that happens after the event. If I show a P300 after an event occurs, I know you were surprised by it because that's the signature pattern for surprise. Abrupt positive voltage. 300 milliseconds, as you probably know, is a little less than a third of a second. But that's consistent. Another one. A negative voltage Okay, you weren't expecting mustard there. I would have known that you weren't expecting mustard there because after you read 400 milliseconds, after you read a word that doesn't make sense in its context, that confusion in everybody is reflected by a negative voltage change 400 milliseconds, almost a half second after the confusing event. And, I want to emphasize, you don't have to put people in any kind of machine. You don't have to stick things into their brain. You just paste it onto their head, and you can pick up enough voltage to detect the event. This is actually kind of an old technology. It's also pretty cheap. We got one that worked with early Apple computers decades ago. We still have it upstairs someplace. It's not some kind of science fiction-y, brand new, high dollar thing. It's just need an amplifier strong enough to show what the voltage is. And lots of events like this have known patterns. Like there's another particular voltage change that signifies that you're expecting an event. There's another one that signifies that an effect, that an event that you expected to happen did happen. There's another that reflects the fact that you're planning to make a movement and what movement you're planning to make. This one is particularly weird because you can set somebody up in a situation where they're going to have to make a choice, and you're going to measure their reaction time to make the choice. So if the light comes on green, press the left button. If the light comes on red, press the right button. You can measure their event-related potential and know what choice they're going to make before they do. You will get access to the plan before consciousness does. Before it gets into their consciousness, you can tell before they can report what it is they're going to do, and that's what they do. I mean, the plans percolate up from the lowest programming centers to the highest programming centers, and before they get into and before they get into consciousness, they've already been worked out by subconscious, unconscious processes that generate electricity. Nothing I know about. See, no consciousness. Okay, I'll just make this the last slide and get into our first directly cognitive topic next time. The event-related potentials have their pluses and minuses too. Plus is they can do things that the imaging techniques can't. They can detect the imaging techniques have to have some time to form the image. Evoked potential techniques can detect events down to the millisecond, which means the thousandth of a second. They're very good at temporal resolution, as we say, meaning time precision. Unfortunately, they're not very good at location. If you have an electrode here, that just means it'll tell you the voltage change, but it could be anywhere in a very large area. They don't even try to pinpoint it. So, this is pretty much where this is all we really need to talk about with regard to neuroscience technology. Of course, there's a lot more to it than this. But basically, some things, in the last 10, 15 years, some things have gotten unbelievably good at detecting location and at generating images. For a lot longer than that, things have been very good at detecting the time course of events. And those two things together have really had some impact on cognitive psychology. Okay, any questions about this? All right, we will leave biology and move on Wednesday.